Hi, in this section 7.6 we're going to take a look at a special function called the unit step function, which is going to make it really easy to deal with a certain class of differential equations that have discontinuous forcing functions, where the external force that's applied to the system is discontinuous. Okay, all right, but before we do that, let me motivate the idea. So let's say that I give you this problem to solve. We have y double prime plus y is equal to some g of t. Okay, I have some initial condition, y of 0 is 0 and y prime of 0 is 0, where g of t, my forcing function, we called it, if you remember from chapter 4, this is called the forcing function of the external force. Okay, and if this is 0, then the equation is homogeneous. If this is not 0, then we call it non-homogeneous. So this is called the forcing function. It could be an external force. Okay, when we did the mass spring example, I referred to it as someone shaking the table, on which the mass lies. So it could be something like that. In this example, we're going to pick a very simple forcing function. We're going to say it's 5 if t is between 0 and pi, and it is 2 if t is greater than pi. Now, this is the simplest example I tried to pick just to motivate this discussion of unit step function. Okay, we've done problems a lot more complicated than this, but I just wanted to pick something really easy so we could run through it quickly. Okay, all right. So how would you solve this problem? Well, I technically have two problems. Once when g is 5, that happens between 0 and pi, and once when g is 2, that happens when t is greater than pi. So I'm going to have to do this problem twice. So let's start with the first one. So I'll say y double prime plus y is equal to 5. That happens between 0 and pi, so I can use this initial condition because this initial condition starts at 0, and this time starts at 0 also. So we have y of 0 is equal to 0 and y prime of 0 is equal to 0. Now, if you go back and look at think about what you did in chapter 4, how did we solve this problem? We first found the homogeneous solution, so let's do that. So we get r squared plus 1 is equal to 0. We get r squared is equal to negative 1, r is equal to plus or minus I. So this tells me alpha is 0 and beta is 1. Okay, all right. So the solution is what? Y is equal to C1, the homogeneous solution, cosine of t plus C2 sine of t. All right, so we are done with the homogeneous solution. Now to find the non-homogeneous solution, we had two methods: undetermined coefficients and variation of parameters. And since this forcing function is really simple, I purposely picked that. Let's go ahead and use undetermined coefficients. So my guess would be what? Since I just have 5, my guess would be just some constant. So if you take derivatives of this, because you take your guess and plug it into your ODE, right? So you get what? Y prime is going to be 0, derivative of a constant is 0, and y double prime is also going to be 0. So if you plug it into the ODE, what do we get? We get 0. We get 0 plus a, because y is this, we're going to plug y sub p in there, is equal to 5. So we get a is equal to 5. So my particular solution is just going to be 5. So my general solution for this first part is C1 cosine of t plus C2 sine of t plus 5. That's my general solution. But I'm not done because I still have to apply the initial conditions. So let's do that. We know that y is equal to 0 when t is equal to 0. So we get 0 is equal to C1 plus 5. So we get C1 is equal to negative 5. To plug in the second initial condition, I need my derivative. So you get negative C1 sine t plus C2 cosine t and derivative of 5 is 0. So we get y prime is 0 when t is 0. That's my second condition. So I get 0 is equal to c2. So c2 is 0. So my first solution is going to be y is equal to c1 is negative 5 cosine of t, c2 is 0, and then we still have that 5. And I'll call it 1 because that's my first solution. Okay. All right. But we're not out of the woods yet because we just did assume that g of t was 5 and we did this problem. And this solution, by the way, is only good if t is between 0 and pi. If t is less than 0 or greater than pi, this solution is meaningless. Okay. So what we want to do now is do the same problem again, but this time g of t is going to be 2. Okay, so let's do that. So we're going to do this problem again. We get y double prime plus y is equal to 2. But what are my initial conditions this time? I had initial conditions before because my value for t started at 0. So I had initial conditions at 0. Now my value for t start at pi, even though pi is not included here, but they start at pi. So I need some initial conditions at pi where we start. So I need to know what is y of pi, and I need to know what is y prime of pi. And why do we do that? So let me explain why we do that. We always wanted solutions to differential equations to be continuous. We always want them to be continuous. Remember what I always tell you, the whole idea of differential equation is to be able to predict what's going to happen in the future. If the solutions have gaps in the future, that's not good because we're not going to be able to predict what's going to happen at a certain time if it has a gap at that time. Okay, so we want our solutions to be continuous. So what we are trying to do here is wherever this solution stops at pi, this guy here, we want this solution to start. You follow? So these two solutions from part 1 and part 2 are patched together at pi. That means they won't have any gaps at pi because that's the only place we're going to have problems. Okay. So what I want to do now is find the value of this previous solution at pi and use that value as the starting value of this next solution. Okay. So let's do that. So what is y1 of pi? Well, cosine of pi is -1. So you get negative 5 times -1 is 5 plus 5. So we'll get 10. So this solution is going to start at 10. What is y prime of pi? So I'll have to take the derivative of that. So we get cosine, derivative of cosine is negative sign. So this will become a positive sine t. And derivative of 5 is 0. So what is y prime of pi? Sine of pi is 0, so we just get 0. So now, using these initial conditions, these two solutions eventually, if we were to graph them, will be continuous and they will be connected at pi instead of having a gap at pi, even though this forcing function has a gap at 5. So if you were to graph this forcing function, which I should have done before, this is my function g of t. Between 0 and pi, it is always 5. So let's say this is 5. So it's always 5 between 0 and pi. And after that, after pi, it's always 2. So let's say this is 2. And after that, it's always 2. So that's what this function looks like. You can clearly see there's a discontinuity at pi. But even though there's a discontinuity, because of the way we are doing this, where this solution ends, the solution begins, there's going to be no discontinuity in our final solution. Okay? So let's finish this problem. Just like before, we're going to have to do this problem twice. So we do the homogeneous problem first. So we get r squared plus 1 is 0. So we get r is equal to plus or minus I, just like before. Alpha is 0, beta is 1. So you get yh is equal to c1 cosine of t plus c2 sine of t. The next thing we want to do is find the non-homogeneous solution. So we guess for a particular solution, we'll use variation of parameters since our forcing function is easy. It's a constant, so my guess is also going to be a constant. This implies that the derivatives are both going to be 0 because the derivative of a constant is 0. If you plug these into the ODE, we get 0 plus a, because y is a, is equal to 2, so we get a is equal to 2. So my non-homogeneous solution, or my particular solution, is 2. So my general solution for this case is c1 cosine of t plus c2 sine of t plus 2. We're still not done because we still have initial conditions to push. We know that y is equal to 10 when t is equal to pi. So those are the initial conditions we're going to use this time, these two. All right. So we get 10 is equal to negative c1 because cosine of pi is minus, sine of pi is 0 plus c2. So we get c1 is equal to negative 8. Okay. Next, we want to plug in the second initial condition, but we need derivative for that. So let's take the derivative. We get negative c1 sine t plus c2 cosine t, and derivative of 2 is 0. We know y prime is 0 when t is pi. So we get 0 is equal to sine of pi is 0, cosine of pi is minus 1. So we get c2 is 0. So now for this case, again, I'll call this y2 because that's my second solution, is going to be, this is my solution. We're going to replace c1 and c2. c1 is negative 8, cosine of t, c2 is 0, so we get plus 2. Now this solution is only good if t is greater than pi. All right. So let's put the two solutions together. So this is going to be my final solution. So we're going to call it y. So we have two solutions. Y is going to be negative 5 cosine of t plus 5 if 0 is less than t is less than pi, and it's going to be negative 8 cosine of t plus 2 if t is greater than pi. So this is my final solution. Now, this was an easy problem, but we still had to go through a lot of work for this. This was the easiest problem I could pick. All right. One of the cool things about Laplace transforms is it's going to let us do these problems where the forcing function is discontinuous in a really efficient way using the idea of step functions. So that's where the step functions come in. Okay. They'll make doing problems like this extremely easy. All right. And these are the kind of problems that electrical engineers deal with all the time. You could have in a circuit, you could have the voltage set at 5 for a certain time, and then the voltage would drop to 2 after a certain time. Or you could have where instead of having 5, you could have 0 and 1, for example. You can think of 0 as off and 1 as on. So you could have the current in the circuit off from 0 to pi, and then after pi, the current comes on. So they mimic stuff. Circuits can mimic stuff like this all the time, where it's on for a certain time or off for a certain time, or where it's a certain value for a certain time and a different value for a certain time. So these forcing functions are going to be discontinuous, and we want to handle these situations in a much better way than what we just did. Again, I do want to stress this problem was extremely easy, but we still had to go through a lot of work. Now let me just check something really quick. Remember I said the whole idea of differential equation is we want continuous solutions. So I want to check what happens at pi. Okay. At pi is included here. We get cosine of, oops, forgot the s, but cosine of pi is minus 1. So you get negative 5 times minus 1 is 5 plus 5 is 10. So this one gives us 10. But let's use the second one and see what happens. What is pi if I use the second function? Cosine of pi is minus 1, negative 8 times minus 1 is 8, 8 plus 2 is what? 10. So you can see the solution has the same value at the point where the discontinuity is. So the solution is going to have no gaps. It's going to be nice and continuous, okay? Which is really important when we solve differential equations. So I hope I have motivated you why we need to study Laplace transforms and step functions, because we do not want to do problems using this technique because it's fairly tedious, okay? So before we can actually learn how to use Laplace transforms and step functions to solve discontinuous forcing functions, solve ODEs with discontinuous forcing functions, let's learn a little bit about the step function, unit step function. The unit step function was developed by a British physicist, called Oliver Heaviside. He came up with this idea of the unit step function. So a lot of the times, instead of being called unit step functions, it's also referred to as the Heaviside function. Okay, and because it mimics on and off behavior, a lot of the time some people also call it the on and off function. So it has many different names. I will always call it just the step function, or if I remember, I will make sure I'll say unit step function, but when I say step function, I refer unit step function. So let's go ahead and define it. So I'm going to write it using two different notations because different textbooks uses different notation, but it's written this way: u of t, okay, is equal to, it is 0 if t is less than 0, and it's 1 when t is greater than or equal to 0. That's what it's defined as. Okay, so let's graph it and see what it looks like. Okay. So we are saying that when t is less than 0, the function is always going to be 0. So it's going to be this. It's going to have a hole there. Okay. And then when t is greater than 0, the function is always going to be 1, including that point. Okay. So the best way to think of a unit step function, if you ever done any worked with binary numbers, in computer science, binary numbers are zeros and ones. If it's 0, we always think of it as off, and if it's 1, we always think of it as on. So you can think of this as the off and this as on. So the best way to think of the unit step function is think of it as off and on. It's off until 0, then it comes on at 0, and it stays on. Okay, when it's on, the value is always 1. When it's off, the value is always 0. So that's an example of a unit step function. Now, like I said, there are different notations. So you can write it as u sub 0 of t. That means it tells you when it comes on. Or you can also write it as this. But again, t minus 0 is just t. That's why I wrote it this way up here. Okay. So there's two different notations. One is using a subscript, and you put down the value, the number where it comes on. And the other one is to write it as a translation here like this. Okay. So that is an example of a step function. Now we're going to take a look at many different variations of the step function. So let's do that. So this was, I'll just call these variations of step functions. Now let's just call it C. Of the unit step function. Okay. So the first variation we're going to take a look at is, instead of coming on at 0 like we did out here, what if it comes on at a different value? Okay, so I'll write it this way: u sub a of t. That means it comes on at a. A could be any number. Or another way to write this is what? U of t minus a. That means we're just translating this function. We're moving it. Remember, we had u of t came on at 0. So t minus a, when we do a horizontal shift, negative means we're doing in the right, we move it to the right direction. So now it'll come on at a instead of coming on at 0. We're shifting it to the right. Okay. All right. So this will look something like this. It comes on at a. So until a, it's going to be 0. Until time a, it's going to be 0. So t is less than a. And after that, it's going to be 1 when t is greater than or equal to a. All right. So if you want to draw a picture for this, you can do that really quick. This is 0, 1. This is a. This is u and t. So this means that it is off until a. That means it's going to be 0 until a. And then it's going to be 1 after that. And you can see why it's called a step function, by the way, I forgot to mention. You imagine you're walking and then you're going to take a step and go up. That's why it's also referred to as and the step is of unit height. So that's why it's called the unit step function. Okay. All right, so that's one example. 2. What happens if I take this step function and multiply it by some other function? Okay, what happens in that case? Well, this function can only, you can only take on two values. Always remember that it can either be 0 or 1. It can only take on two values. So until a, this function is going to be 0. So if you take 0 times f of t, you're going to get 0. So 0 until a, when t is less than a. And to the right of a, the function will take on the value of 1, you will. So if you take f of t and multiply by 1, you just get f of t when t is greater than or equal to a. So that's what that happens. Always remember, you can only take on two values, 0 and 1. It's always 0 to the left of a, and to the right of a, it's always going to be 1. All right. Let's take a look at a different example. What happens if I take u of a minus u of b, u sub b? So what does this mean? This one comes on at a, and this one comes on at b, and you're subtracting them. What's going to happen? This, okay, so let's take a look at that. So let me graph this one, and then I'll write down what's going to happen. So let's graph this one. So let's say a is here, and b is here. This is t, this is u, and this is 1. I'll use two different colors to mimic each one. I'll use blue for a and green for b. Okay. So until t is equal to a, this first function is going to be 0. So it's going to be 0 until a. Then it comes on at a. So it'll become 1. Okay, so that's the first function. Let's take a look at the green one. The second function comes on at b. That means until b, it's going to be 0. And then it comes on at b. And it's going to become 1. Because remember, I told you, you can only take on two values, 0 or 1. Now what are we doing to these two functions? We are subtracting them. So what will happen? So let's take a look at that. Well, to the left of a, if I subtract the two functions, both their values are 0. So 0 minus 0 is going to give you 0 if t is less than a. Okay. What happens to the between a and b? Well, between a and b, the blue function is 1 and the green function is 0. So if you subtract the two, you'll have 1 minus 0, so you'll get 1. So that is between a and b. What happens to the right of b? Well, to the right of b, what do we have? The green function is 1 and the blue function is 1. You can see they're both exactly the same. So if you subtract them, you get 1 minus 1, so we get 0. Okay, so that's what we end up with. Now, these inequalities that you have, technically this should be less than and this should be equal. And that's not really important, and you'll see later. So don't worry so much about where it's equal or something. Just make sure you know the general values of those functions in those intervals. Okay. So this is a really nice example, because what does this mimic? It basically tells you that if you want a function to be on between two time stamps, between two time values, then all you have to do is subtract the two values of the step function there, because everywhere else it'll be 0 and it'll just be on for that between those two values. So you take u of a minus u of b, basically means that it's on between these two time values a and b. Everywhere else it's 0. So we can use that idea to do this last variation. I can have f of t times u of a minus u of b. So what does this mean? What does this do? Like, what did I just say? When you have u of a minus u of b, that basically means that this function is going to be 1 between a and b. Everywhere else it's going to be 0. So if it's 0 everywhere else, when you multiply f of t by 0, you're going to get 0. So you're going to get 0 when t is less than a. It's going to be f of t. Why is it going to be f of t? Because between u of a and u of b, this is going to be 1. So f of t times 1 is just that, between a and b. And then it's going to be 0 for this. Okay. So this is the main thing for us going forward. We're going to need this one. We're going to use this one the most. Okay. So I gave you some variations of the unit step function. So let's put them in play. So we have two types of problems that we can deal now. Okay. So the first type of problem is we want to write a piecewise function as a step function, as a unit step function. So that's the first type of problem. So let's take a look at two examples of that. So let's say if I have f of t is 1, actually let's use the problem that we started with, 5, if t is between 0 and pi, and 2 if t is greater than pi. This is a piecewise function because you have two pieces. This is the first piece and the second piece. Okay. Now what we want to do is write this as a step function. So let's do that. So what is f of t? Well, let's pay attention just to the first piece. When is this piece 5? Between 0 and pi. That means, think about it. I want this value of f of t to be 5 when t is between 0 and pi. So I want this function to be on between 0 and 0 and pi, and everywhere else I want it to be off. Okay, and when it's on, it's going to take on a value of 1, and if you multiply by 5, it'll give you the value of 5 that you want. So I'm going to write it as 5 times u of 0 of t minus u of pi of t. Now before I go any further, let's try this. Well, according to what I gave you earlier, whenever we take the difference of two step functions, that means it's going to be on between 0 and pi, and everywhere else it's going to be 0. So between 0 and pi it's going to be 1, and everywhere else it's going to be 0. So if you take to the left of 0, if you multiply by 5, you're going to get 0. Between 0 and pi, since this difference is 1, if you take 5 times 1, you're going to get 5. That's between 0 and pi. That's correct. And to the right of pi, this difference is going to be 0. So if you take 5 times 0, we just get 5. So this can be written this way. Okay. But we're not done because we still have to worry about the second piece. So let's do that. Okay. So the second piece is on when it's greater than pi. So we go plus 2 times u of pi of t. So let's see if that makes sense. Well, what does this mean? This means that this piece comes on at pi. That means until pi it's 0, and after pi it's 1. That's what u is. So if you, to the left of pi, if you take 2 times 0, you get 0. And to the right of pi, 2 times 1 will give you 2, which is what we want. To the right of pi, we want it to be 2. 2 times 1 will give you 2. Okay. So we've written this piecewise function that had two pieces using just one function. You can see that there's no pieces here. That's the power of unit step function. I can do a little bit better with this though. If you notice, there's certain step functions that are the same here. So I'm going to combine them. So I'm going to go ahead and distribute here first. I get 5u of 0. I'm not going to write t's anymore. Minus 5u of pi plus 2u of pi. So we get 5u of 0 minus 3u of pi. So this is the final product that we are looking for. Okay, we haven't done anything fancy with this yet. All we are doing is writing a piecewise function as a step function. Eventually, we're going to take the Laplace transform of this because we want to use Laplace transform to solve a discontinuous forcing function. But for now, we just want to master how to write them as step functions. Let's take a look at another example. Let's say if you have f of t, let's take a look at one that has multiple pieces. It is minus 1 if t is less than 0. Okay, actually let's make it interesting. 0 is less than t is less than 1, and then it's 2t if 1 is less than t is less than or equal to 2, and it is t squared if t is greater than 2. So this is a piecewise function. It's discontinuous. We want to write it as a step function, and when I say write it as a step function, we want to write it as a single function. You can see what we did here. Okay, so let's start. F of t. So the first function comes on at 0 and stays on till 1, and after that it's going to be 0 again. Okay, because the first function is going to have the value of -1 between 0 and 1. So that's all we care about. After that, what happens before 0 and after 1, we don't care. We just want to make sure that it's always going to be -1 between 0 and 1. So the way we do that is we write u of 0 minus u of 1. This tells you that this is going to be 1 between 0 and 1. Everywhere else it's going to be 0. So if you multiply this by -1, you'll get that value of -1 between 0 and 1. Plus, this piece comes on between 1 and 2. So between 1 and 2, this is going to be 1, and everywhere else it's going to be 0. So if you want the value of 2t between 1 and 2, you just multiply it by 2t, because if you take 2t times 0 before 1, you'll get 0. 2t times 1 between 1 and 2, you'll get 2t, which is exactly what we want, and after that it's going to be 0. And then the last piece always stays on, so you get t squared times u of 2, because that's just until 0 this function is 0, and to the right of 2, until 2 this function is 0, to the right of 2 it's 1. So if you multiply t squared by 0, we get 0. So to the left of 2 it's always going to be 0, and to the right of 2, when you multiply t squared by 1, you'll just get t squared, which is what we want. Just like before, we can distribute and clean this up, so you get negative u naught plus u1 plus 2t u1 minus 2t u2 plus t squared u2. I'm just distributing these. Let's collect what we can. So you get negative u naught. I have a u1, so I can combine those. So we get plus, I can take out a u1 from these two terms. So I'm left with 1 plus 2t. Out here, both of these have u2 in common, so I can take out a u2. And I'll write the positive, this t squared first because it's positive. So I get t squared minus 2t. And this is f of t. So we started with a function that was discontinuous, and it was a piecewise function, and we wrote it using multiple pieces. Okay. Now, so this is what we're going to do. We'll be given a discontinuous forcing function, like either like this or like this, and we want to write it as a step function so that we can write it as a single function. Then we can take the Laplace transform of this and deal with those types of problems very easily. But the second type of problem we're going to have is where we want to write the unit step function as a piecewise function. So we want to do the opposite of what we just did. So let's take a look at two examples of that really quick. Okay, so let's say that I have been given, I'll call this g of t. G of t is equal to, I have u of 0 plus t squared minus 1 u of 2. So they've given us a step function, and we want to write it as a piecewise function. So let's do that. So we have g of t. The two times are given to you, 0 and 2. Those are the two times we are working with. So let's just draw a little region. I have 0, 2. I have the region to the left of 0. I have things happening between 0 and 2, and then to the right of 0. Now normally we don't really care about anything to the left of 0. Why is that? Because t represents time usually, and time cannot be negative, so we'll start everything. So we really only have two regions. We have this region, 0 and 2, and greater than 2. So let's do that. So 0 is less than t is less than 2, and t is greater than 2. All right. Now what happens in those regions? Well, let's take a look at that. when t is between 0 and 2, okay, what's going to happen? If t is between 0 and 2, u of 0 is going to be 1, because anything greater than 0, it's 1. And u of 2 is going to be 0. Do you agree? Because this one does not come on till 2. So prior to 2, it's going to be 0, because you can only take on two values, 0 and 1. So what is the answer? So we'll get 1 plus 0. So this value is going to be 1. Okay. All right. What happens greater than 2? When t is greater than 2, remember this came on at 0 and it'll stay on. So if it's greater than 2, this is still on, so it'll be 1. This comes on at 2 and will stay on. So after 2, this will be on, so it'll be also 1. So we'll get 1 plus t squared minus 1, because if you take t squared minus 1 times 1, you just get that. Ones will cancel, so you'll get t squared. So this is the corresponding piecewise function. Okay. Eventually, when we use Laplace transforms to solve these discontinuous forcing function, your solution is going to look like this. So you want to write it as a piecewise function. You always want to write your final solution without the step functions. Okay. All right, let's take a look at one more example of that. So let's say if we have g of t is equal to 5 plus t minus 5 u of 3 plus t cubed minus t u of 8. All right. Oops, I forgot. If you just have a constant, like I have 5 here, and if you don't have a step function, then that step function is supposed to be u of 0, just so you know. Okay. So if you don't have if you just have a constant without the step function, then that step function is going to be u of 0. So what are my times? I have 0, 3, 8. So let's draw a little timeline. I have 0, 3, 8. Like I said, we don't care about values to the left of 0. So I have how many regions here? 1, 2, and 3. So let's split up piecewise functions into 3 regions. 0 is less than t is less than 3. And don't worry about the equalities where they are. Just make sure if you put any, you don't write it this way. That means that makes no sense, because this is equal to 3, this is equal. If this is equal to 3 here, then get rid of the equality here. Okay, just do it that way. And then this is t is greater than 8, since I already said equal here. Or I could do this. I could say this is less than and this is greater than. It doesn't matter. Okay. So I got my 3 time regions for time. Now we just need to figure out what are the values of each of these functions in each of those regions. Between 0 and 3, which of these functions are going to be on? This one does not come on till 3, so it's going to be off between 0 and 3. This one does not come on till 8, so it's going to be off. So the only one that's on between 0 and 3 is the first one. So the value is going to be 5. Now what happens? Between 3 and 8, what's going to happen? Once this one comes on at 0, it stays on. Okay, so this is going to be 1. This one comes on at 3, so between 3 and 8, since it's greater than 3, this one's on. And this one does not come on till 8, so it's still off. So we'll end up with what? 5 plus t minus 5 times 1 is t minus 5. The 5's cancel, we get t. And then the last function, the last region, t is greater than 8. If t is greater than 8, this one is still going to be on because it came on at 0 and stays on. This one came on at 3 and stays on, so it's still going to be on at 8. And this one comes on at 8, so this is 1. So what do we have? We have, in here we'll have what? 5, because 5 times 1. T minus 5 times 1 is t minus 5, plus t cubed minus t, because times 1 is that. The t's cancel, the 5's cancel, so we get t cubed. Okay, so that's what we end up with. Okay, so we did a couple different variations of these examples. One is where we took a piecewise function and wrote it as a step function, and the next is we took a step function and wrote it as a piecewise function. You need to have the ability to do both, because when you start a problem, when you solve a discontinuous forcing function problem, when you start a problem like this, your first goal is to write it as a step function. And when you end a problem, after you get done solving using Laplace transform, you'll end up with something like this. So you want to write it as a piecewise function. So you want to end with that. So you're going to use both of these techniques later. All right. So now that we did that, let's take a look at how to find the Laplace transform, because eventually we want to use Laplace transforms to do this, right? So how do we find the Laplace transform of a unit step function? Okay, so we want to learn how to find the Laplace transform of a unit step function. So we're going to take a look at many different variations of this too. So let's start with this. What is the Laplace transform of u of a? Something that, a step function that comes on at a. Another way to write this is what? Laplace transform of u of t minus a. Same thing. Okay, I'm just using the shortcut notation. A lot of books use that. Our book uses this notation, but I prefer writing the other one. All right. Since we've never done this Laplace transform before, we're going to start with the formal definition of Laplace transform, which is this: 0 to infinite. We have e to the minus st times u of a dt. This is the formal definition. All right. So what does this mean? Well, but wait a minute. If you look at this function, how does it behave? It comes on at a, so until a, this function is what? 0. And then after a, it becomes 1. So I can split up this integral, this definite integral, from 0 to 1. I get e to the minus st. This u is going to be 0. Oops, e to the a, not 1. Because until a, this u function is 0. Plus, from a to infinite, this u function is just 1. So I get this. So I'm just splitting up the integral. So we end up with that. This is just going to be 0 because of this. So we end up with the integral a to infinite. I'll use limit notation. I get limit. It's an improper integral. B goes to infinite. We're going to a to b, e to the minus st times dt. That's what we get here. Well, this is a very simple integral to do. Integral of this is you do a u substitution for minus st. So we end up with limit as b goes to infinite. We're differentiating with respect to t, so keep that in mind. So you'll get e to the minus st over negative s from a to b. So we plug in the upper limit. So we get 1 over negative s e to the bt. I just moved it to the bottom, made this negative exponent positive, plus 1 over s e to the minus sa. Oops. Actually, I'll leave it on the top. Let me do that. I get e to the minus sb over minus s plus e to the minus sa over s. This positive this positive comes from the fact that this is negative and you're subtracting the lower limit. All right, what is this limit? Well, if you think about it, we have two options. Okay, let me do that on the side. I don't have room on the right, so I'm going to do here it on the left. I can write it as this 1 over, this s is a constant. We're taking limit with respect to b, so this s has nothing to do with it. So I'll just write it as sb. I'm just moving this negative exponent down. As b goes to infinite, this will go to infinite, so this whole fraction will go to 0, provided s is greater than 0. Because if s is greater than 0, this will happen. If s is less than 0, then what will happen? So let's take a look at that just to show you. I have e to the minus sb. Now remember, if s is less than 0, that means this s here is negative, less than 0. So this negative in the front will make it positive, so this exponential term, the exponent, is going to be positive. So as b goes to 0, infinite, this will go to infinite. And we always want our improper integrals, when we use the Laplace transform formula, we want our improper integrals to converge. We don't want them to diverge. When it goes to infinite, it's going to diverge. So if s was negative, this term here would be negative, and this negative in the front would make this whole exponent positive. So if it's positive, this e term will stay in the numerator, and then e to the infinite will give you infinite, and that means this improper integral will diverge. So what we want is, we want the s term to be greater than 0, so that way if s term is greater than 0, then we have something like this. If this is greater than 0, that means it's positive, so positive times negative, this whole thing is going to be negative, so we can move it to the denominator. Okay, so now this is positive, so e to the positive infinite is infinite, and 1 over infinite is 0. That's how we get that. Okay, all right, we've done this in 7.2. I just wanted to quickly review that. So we're going to say that this is going to go to 0 provided s is greater than 0. So if that happens, what am I left with? What is the Laplace of u of a then? You're just left with this e to the minus sa over s. This is when s is greater than 0. So this is a new Laplace you have to memorize, just like you did with some of Laplace of cosine, Laplace of sine, and so on. Let me just quickly give you an example of this before I move on. So let's say someone comes and says, what is the Laplace of u of 3? That means the same as what? What is the Laplace of u of t minus 3? Isn't that the same thing? According to this, a is what here? 3. So in this, you replace a with 3, so we get negative 3s over s. That's what you end up with. Okay? All right. Let's take a look at the next Laplace that we need. Now this next one, we're not going to see when we do Laplace, when we take the Laplace, but we're going to see when we do the inverse Laplace. So that's the only reason why I'm doing this. Okay, so you have u of a. Another way to write this is what? F of t minus a times u of t minus a. So we want to find the Laplace of this. What is special about this? This means a translation. So you take the function u of t and translate it into what? U of t minus a. Move it to the right by a units. So we are moving the u function to the right by a units, and we're also moving the f function to the right by a units. So these two values are identical. Okay. Now, that's never going to happen when we do Laplace transforms. Do you guys follow? Because when we end up, like for example here, okay, actually that's not a good example here. This is u of t minus 1, right? Because it comes on at 1, t minus 1. Are these written as, like, if we had 1 plus t minus 1? We're not writing it that way. Same thing over here. This is u of t minus 2. Are these all written as t minus 2 squared minus 2 times t minus 2? No, that's not going to happen. So our function f is not going to always have the same translation as u. So keep that in mind. So that's not what we have here. We have the function f has the same translation as u. But like I said, the reason why we are doing this Laplace transform is for the inverse Laplace transform. Okay, so let's do this. So let's start with f of t minus a u of a. So this one comes on at a. All right, so that means we can split this up just like I did before. From 0 to a, this function is going to be 0, and after that it's going to be 1. So from 0 to a, we get e to the minus st times 0, because it'll be f of t minus a times 0 is going to be 0 dt. Actually, let me go ahead and write f also just for completeness. T minus a, and this u is going to be 0 dt. Plus, from a to infinite, we get e to the minus st f of t minus a 1 dt, because after a, u is going to be 1. So we're going to end up with this. This whole thing is going to be gone because of the 0. So we're going to end up with a to infinite e to the minus st f of t minus a dt. So how do I integrate this? Well, it is a composite function because the inside is t minus a. So usually when we integrate functions that are composite, we start by substituting for the inside. So let's do that. So let's call that u. U is equal, well, I don't want to do u since we have a step function called u, so let's not do that. Let's call it z is equal to t minus a. So what is dz? dz is going to be just dt because a is a constant. So we got done with that. But what happens, I want to change these limits. These limits right now reflect the variable t. What happens, I want the limits for variable z. So what happens when t is equal to a? If I replace this t here with a, we get a minus a, so z would be 0. What happens when t is equal to infinite? You'll get infinite minus a, which is still going to be infinite. So we got that done. What about t itself? If we do back substitution, what is t then? It'll be z plus a if you solve for t. Alright, so let's use all of those to rewrite this integral. We get a, not a, because z is going to be what now? 0. So we're going to go from 0 to infinite. We get e to the minus st. What is t? T is z plus a, f of z dz, because that's what we get. Now you might go, why do I go through all of this work? You'll see in a second why. If you notice, e to the minus st z plus a can be written as e to the minus sz plus minus sa, and you can write it as e to the minus sc times e to the minus sa, just using exponentials. Okay. We are taking integral with respect to z. This has nothing to do with z, so it's a constant. We can pull it out. So that's what we're going to do. So we get e to the minus sa, the integral 0 to infinite e to the minus sz f of z dz. Now this should look familiar, this integral. Isn't this the definition of Laplace transform? Except instead of a t we have a z, but it is exactly the definition of a Laplace transform. So what does that tell me? The Laplace transform of f of t minus a u of a is equal to e to the minus sa times, how do we write Laplace transform? I can write it like this, script little f, or I can also write it as big F of s. So those are the same things. So this is really cool because, like I said, we are not going to be taking Laplace transforms of function like this, but we are more interested in the inverse Laplace transform. But let me box this anyway. So this is the Laplace transform of f of t minus a and u of a. U of a is the same as u of t minus a. But more important to us is the inverse of this. Okay, what happens if I take inverse Laplace on both sides? These will cancel, so you'll get that. So this gives me a new formula. It tells me inverse Laplace of e to the minus sa times big F of s is equal to f of t minus a times u of a, which I'm going to write it as t minus a this time. And I'll explain why. I could have written it as u of a, but I'm going to say why. If you recall, in section 7.3 I gave you this. We did this. We call e to the at f of t. If you take a function and multiply it by an exponential and take the Laplace of that, what does that do? That shifts the Laplace of this function, which is at big F, in the s domain by a units. It shifts it, if you recall that. And we call this the first shift theorem. You can go back and look through your notes. This is from 7.3. Okay. This is exactly the opposite of that. Now we're taking the transform. Remember, out here we took the function and multiplied it by an exponential. Now we're taking a transform and multiplying it by an exponential. Do you guys follow? So in this case, what happens? When we do that, we always introduce a step function, and then we also do a shift in the t domain. So two things happen. Out here only one thing happened. We just did the shift in the s domain of the Laplace of this guy, big F. Out here, we take the inverse Laplace of this f and shift it in the t domain, and then also multiply it by a step function. So it's a little bit more complicated. And this is actually called the second shift theorem. And this is going to be extremely useful to us. When we do inverse Laplace, this is going to be extremely useful to us. Okay. So please memorize that. That's going to be extremely useful. Just like I asked you to memorize this one, you should memorize this one, and you should memorize this guy. So those are the ones that we are basically going to be working with a lot. Okay. All right. So I did that. But I told you, most of the time, like I said, this Laplace is really quirky because we are saying that the function has to be translated the same as the step function. That's never going to happen. I showed you earlier. Most of the time our problem is going to be like this. We'll have some function times a step function that's translated. Okay. So in that case, how do I find the Laplace of that? I know what the Laplace of this is. How can I use that to find the Laplace of this, which is what I really need? So let's do this last Laplace. Okay, did I do 1, 2, 3? Yep. So the last thing we're going to do is we want to find the Laplace of f of t times u of a. Another way to write that is what? F of t times u of t minus a. Okay. So to do this one, we're just going to use this property 2. This is property 3. We're going to use property 2 of Laplace of step functions to use this. So I'm going to start by making a substitution. Okay. I'm going to go let g of t equal to f of t minus a. So in this property 2 here, I'm going to call this g of t. And now that I did that, I realized something. I want to call this g also. Okay. All right. So if I do a translation here, if I go t is equal to t plus a, I replace this t with t plus a, replace this t with t plus a, I get g of t plus a is equal to f of t. I'm just doing a translation. Okay. So what happens by property 2? So by property 2 that we just did, okay, we get this. We get the Laplace of g of t. Remember in property 2, actually let me write property 2 down, maybe that'll help. We get this. We have f of t minus a times u of a is equal to e to the minus s a, okay, times big F of s. Okay. But what's another way to write big F of s? Well, another way to write big F of s, isn't that the Laplace of little f of t? Okay, so that's what I have. So now I'm going to replace this with g of t. I get u of a is equal to e to the minus sa times the Laplace of f of t. What is f of t? F of t is right here. It's g of t plus a. So we end up with that. Now this is extremely important to us. Okay, so please bear that in mind. This is extremely important to us. This is what we are going to be dealing with, functions like this. All right. So this is one you should memorize when we want to do Laplace involving step functions. So let's take a look at some examples of this last property. So let's say that if I give you this, find the Laplace of, okay, e to the t times u of 3. Okay, or another way to say this is what? Find the Laplace of e to the t times u of t minus 3. Okay, so let's do that. So this is like my f of g of t, right? Okay, so let me actually write down. So I have my g of t is equal to e to the t, and my a is equal to 3. Okay, so what does that give me? I need the Laplace of g eventually. Okay, but it's a g that's translated. It's t plus a now. Not just t, but it's going to be t plus a. So let's see what we get. Okay, so if I use this, let me write this to the left. You guys don't need to erase it. I'm just going to write it to the left so I have room. So I get e of t. That's my function g, and my a in this example is 3. So I get Laplace of e to the t u of 3 is going to be e to the minus sa, a is 3, so it'll be 3s, times the Laplace of the function g that shifted as follows. So instead of t, we have t plus a. So this is my function g, so I'm going to write it as what? E to the t plus a. So we're going to take the Laplace of that. So let's do that. We get e to the minus 3s times, by the way, what is this? You have e to the t plus 3. Isn't that the same as e to the t times e to the 3? This is a constant, so we can pull it out. And we are left with just the Laplace of e to the t. You should know the Laplace of e to the t. What is the Laplace of e to the t? It's s minus 1, because a is 1 here for this Laplace. And these I can combine, add the exponent, so we get e to the minus, I can take a 3 out, s plus, actually I'll just write it as minus 3s plus 3. So that is the Laplace of this function. Okay, we did that translation there. Let's do another example. Let's say that I want to find the Laplace of t squared u to the 1. Okay, another way to write this is what? Laplace of t squared u t minus 1. And you can see why we cannot use property 3, property 2. To use property 2, which is this property, the function and the step function have to be translated at the same point, t minus a, t minus a. Is that what I have here? I have this is translated to t minus 1. How about this one? If this was t minus 1 squared, yes, then I could have used property 2. But that's not going to happen. Most of the time it's just going to be some generic function in the front which is not translated. So that's why we needed property 3 to help us with that. So in this case, g of t is t squared and a is 1. So the Laplace of t squared u1 using property 3 is going to be e to the minus sa, a is 1, so you get e to the minus s, times the Laplace of the function g shifted. But also keep in mind, we are doing a positive shift here, okay? So keep that in mind. So I'm going to shift the function g. So g is t squared, so it's going to be what? T plus 1 squared. So now all we have to do is expand it and do Laplace transform term by term. So let's do that. So we get e to the minus s. What is the Laplace of t squared? It's like t to the n. Laplace is what? It is n factorial over s over n plus n, s raised to n plus 1. In our case, n is 2, so we get 2 factorial, which is 2. You get s cubed plus 2 over s squared plus 1 over s. I just did these. If you did chapter 2 and section 7.2 and 7.3, you know how to do that. So this is the Laplace of t squared u of 1. And you can see it's fairly easy to do. Alright, let's finally do 2 more examples and we'll be done with this video. I still haven't even scratched the surface on how to do this, but I'm sure this video is already getting long. Okay, so I want to just do 2 more examples and wrap this up. Okay, so let's say we have g of t is equal to 2, 0 is less than t is less than pi over 2, and sine of t if t is greater than pi over 2. Now this is a piecewise function. They want us to find the transform of this. So the question is, find the Laplace transform of g of t. Well, if I want to do that, I don't know how to take a Laplace transform of a piecewise function unless I'm going to use the formal definition. So if I wanted to do that, I could have done this 0 to pi over 2 e to the minus st times 2 dt plus from pi over 2 to infinite e to the minus st times sine of t dt. So I'm using this right here, and then I would have to integrate, and that's a lot of work. I do not want to go through that much work. So that would work. But now to do this, I can do it faster because I learned earlier how to write g using step functions, and just now we learned how to take Laplace transforms of step functions. So we can do those two together. So we'll do it in two parts. First, we're going to write g using step functions. This first piece is on between 0 and pi over 2. So it'll be u of 0 minus u of pi over 2. So it'll be 2. The second piece is on after pi over 2. So u of pi over 2 times sine of t. So that's the first part, writing it as a step function. We did that. Now we're going to take the Laplace of this. So if you're going to take the Laplace of g of t, so I'm going to take the, oops, I'm sorry, getting ahead of myself. Let's go ahead and distribute and clean this up. We should always combine the steps functions that are the same. So we can write it as u of 2u naught plus sine of t minus 2 u of pi over 2. So this is g of t in step functions. Now we want to take the Laplace of this. So we'll take use 2 as a constant times the Laplace of u naught plus the Laplace of all of this, sine of t minus 2 u of pi over 2. All right, this is property 1 that I just gave you, Laplace of u of a. Okay, if you remember, Laplace of u of a was what? E to the minus sa over s. In our case, a is 0. So this is 0, e to the 0 is 1, so you'll just get 1 over s. Okay, so this gives you 2 over s plus, for this one, I have some function times a step function. This is property 3. So this we call g of t, if you recall, and a is pi over 2. So what do? We get e to the minus as, so minus pi over 2s, times the Laplace of the function g shifted by plus a. So wherever you see a t, you shift it by plus a. Write it as t plus a. So a is what? Plus pi over 2 minus 2. Now we're almost done. We get 2 over s plus e to the minus pi over 2s times, what's the Laplace of this? Well, Laplace of sine is what? We know Laplace of sine t, but do we know Laplace of t plus pi over 2? No, we don't. So we need to fix that. So let's take a look at that. What is sine of t plus pi over 2 from trig? It's a sum of sine of the sum of two angles, right? It's sine of t cosine of pi over 2 plus sine of pi over 2 cosine of t. We know cosine of pi over 2 is 0, sine of pi over 2 is 1, so this just gives you cosine of t. So this really is just cosine of t. Okay, let me write it this way. So this is just cosine of t. So what is Laplace of cosine of t? We definitely do know that, so let's use that. So Laplace of cosine of t is just s over s squared plus 1, b is 1 here, minus Laplace of 2, Laplace of a constant is just 2 over s, and there is the Laplace of the function g of t. Okay, let me do one last example of something what I just did. So what is the Laplace of, I'm sorry, let's create the function f of t. I have t and t squared, 0 is less than t is less than 1, and t is greater than 1. Okay, so we want to find the Laplace of f of t. This is a piecewise function. The only way I can find the Laplace of a piecewise function is by using the formal definition, the integral definition, which I want to avoid. So the next thing I want to do is, if I'm going to use shortcuts, the first thing I have to do is write f of t as a step function and then take the Laplace of that. This first piece is on between 0 and 1. So we get u of 0 minus u of 1 multiplied by t. Plus the second piece stays on after 1. So we get t squared. I can distribute and clean this up. So we end up with t u naught plus t squared minus t u of 1. So this is f of t written as a step function. Now we're going to take the Laplace of this. So we get Laplace of t u naught plus the Laplace of this, t squared minus t times u1. So in the first case here, g, this is my function g, and the a is 0. In the second case, this is g and a is 1. Okay, so using property 3 that I just gave you, we get e to the minus as. A is 0, so e to the 0 is just 1. So we just get 1. Laplace of, you're going to shift g by a unit, so you just get Laplace of t. If you get t plus 0, it's just t. Out here you're going to get e to the minus as. A is 1, so you get minus s times the Laplace. You're going to shift g by 1 plus 1, so you'll get t plus 1 squared minus t plus 1. So wherever we see a 1, remember we get f of t plus a. So we're going to, instead of just having f of t, we have a plus a here, and a is 1. So wherever you see a t, replace it with plus 1. So Laplace of t is what? 1 over s squared plus e to the minus s times the Laplace. I'm going to expand this. I get t squared plus 2t plus 1 minus t minus 1. The 1's will cancel. The t's will get combined to just a t. So we'll end up with 1 over s squared plus e to the minus s. Laplace of t squared is what? 2 over s cubed. And remember, this 2t and this negative t will just give you a single t, so you'll get plus 1 over s squared. And that is the Laplace of f of t. So far, we've just learned what a step function is, how to take Laplace of a step function, how to write a piecewise function as a step function, how to write a step function as a piecewise function. Now, next lecture, we'll take all of these tools and combine them and use them to solve differential equations that have discontinuous forcing functions. Okay.